Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 30 of our electrical machines subject. So in the previous lecture we discussed about armature reaction, what kind of effects armature reaction cause and like what are the different cases, right, when armature reaction will be present. So today's lecture will be mainly on improving the armature reaction. So whatever armature reactions, whatever extra flux we are getting in the armatures, right, we will try to nullify those using techniques. So we learn those. There are mainly two techniques that we use. One is the interpoles, another one is the compensating windings. So first we will discuss about interpoles. Interpoles are also called as commutating poles, where what we do is beside the two main poles, right, we place another two poles which are called interpoles. Okay, now what are those? So interpoles are small auxiliary poles between the main poles on the q axis. Okay, so the d axis, direct axis of the main pole is here, right? Q axis will be 90-degree perpendicular. So perpendicular to the main poles I will place my interpoles strategically. Why? They are placed strategically just to remove the additional flux that has been generated by the armature conductors. Okay, they won't with conductors carrying the armature current connected in series with the armature. So interpoles are connected in series with the armature, hence what will be the mmf produced? So mmf produced will be an interpole into IA, because those windings are in series with the armatures. That's why the current that they take is IA current. Why I want IA current? Because I want to cancel out the same MMF, right, that has been produced by the armature. To simplify our things, that's why I try to make them in series with the armature. Now, what shall be the polarity of the interpoles? Because I want to cancel out my armature reaction, what shall be the polarity? Like whether this should be north pole or south pole. So their polarity will be same as the next pole ahead in the direction of rotation in case of generators. So in case of generators, the polarity, if my generator is rotating in the clockwise direction, then what is the next pole ahead? South pole. So interpole also should be south pole. Like we will see it using diagrams, using the waveforms, why actually south pole helps here and north pole will help here. We will see this, we will prove it, don't worry. Okay, so just remember this thing: interpoles in case of a generator, uh, the polarity will be same as the pole ahead of the next pole, that is south pole, right? In case of motor, it will be just the opposite for motors. So function, they produce a localized flux. So this interpoles will produce a localized flux. Why localized? Because if you see the pole tip, right, is very thin. So it's not like they will like produce flux throughout. No, they are there for a purpose. They are there to cancel out the flux in the q axis, right? Because the q axis is the axis where the main flux is there. So if you remember, when what was the overall direction of the flux, right? If you remember, overall direction of the flux was something like this. In case of generator, the overall flux was somewhat like this. Okay, so of course I have to cancel out this overall flux along the q axis. How will I cancel it? Simply place a north and south poles that is projected only in this region, so that this flux direction will be opposite to the armature reaction, so it will cancel it out, right? So that is the main purpose of interpole. Very simple to understand, very simple to understand. Okay, so they will produce, they improve the commutation by keeping the MNA fixed. So what happens? As the flux is nullified, so there will be no shifting of MNA, no shifting of MNA as flux gets nullified. Okay, now neutralize armature reaction during commutation. Okay, so of course it will neutralize armature reaction during commutation, so there will not be any reactance voltage, right? Because we discussed, right, another drawback was not proper commutation. So if the armature reaction has been cancelled, so proper commutation will happen, so it will neutralize the reactance voltage due to commutation problem, right, which was happening previously. Okay, so these are the main things that our like interpoles does, right. So now we will see graphically how actually it neglects. So pictorially you have understood. So overall flux direction is in this direction. So I'll just place a north south pole. The pole show will be very thin, narrow, so that I only affect this region. I don't affect the other regions because I don't want to mess up the flux distribution in the other regions. I only want to focus on this region. Okay, so that's the thing basically. So without interpoles, so this is the graph of without interpoles. So without interpoles, basically, what is the resultant flux? If you remember, the resultant flux was somewhat like this. The resultant flux was like this, was more down here. Then the, of course, the zero crossing has been shifted. Then it went up. The peak value also increased, right? Peak value also increased. The zero crossing also got shifted to be more negative. Okay, and so on. Correct. Not like this, like this, something like this. Okay, so this was the flux, this was the resultant flux without interpoles. Now with interpoles, what will happen? With interpoles, okay, so with interpoles, basically what I can say is extra additional flux will be generated along the q axis. So this is the q axis, this is the q axis. So this will be here opposite to the armature flux, right? If armature flux is positive, this will be opposite. If armature flux here is negative, this will be positive. Okay, direction will be opposite to the armature flux, as can be seen here, right, to cancel out the armature reaction. Okay, so basically if you now if you see, and it is localized, right, it is only present here, very narrow. It is not present throughout the mechanical angle, it is only present in this particular region, right, very narrow. So it is localized. Okay, so these are all localized. Now if I plot the resultant, what will happen? Previously the flux was here, but I am adding something positive, so the flux will be somewhere here near the zero crossing only. Okay, so now the resultant will be somewhere, starting somewhere from here, right, but the rest won't change, this portion won't change. Again here, right, I have a negative here, so the peak value also kind of will change. Okay, not the peak value, so when, no, not peak value will be like this only, peak value will be same. Now as it goes down, right, it will go down very sharp, because here suddenly there is bit of negative flux. So the zero crossing, like ultimately our aim is to not change the zero crossing, right. So again it will, the peak value will be there, again it will try to reduce, and then again there will be sharp reduction, and zero crossing will be same as the previous zero crossing, because there are interpoles here. So ultimately what happens, interpoles can compensate the armature reaction. Now sometimes what will happen, they can overcompensate the armature reaction, right. That is also another problem with interpoles. What can happen, interpoles can overcompensate, that is, if this flux is more positive, then zero crossing will be more ahead. Okay, that is kind of a thing that we might also want to do, because we want to improve our commutation further. Okay, so yeah, this is about it. So polarity of interpoles, you can read why it matters, all those things we have discussed. Why series connection with armature? Since armature reaction is proportional to armature current, interpole mmf also should vary proportionally, because armature reaction is what? If armature current is higher, more magnetic flux will be generated by the conductor. So we want to cancel out the same flux, right? So that's why, as the armature mmf is proportional to the armature current, so we want our interpoles also, the field current of the interpoles also should be the same as the armature current. So hence interpoles are connected in series with armature so that their field strength automatically adjusts with load variation, because if the load changes, then the armature reaction also value will change. But if, let's say, the interpole current was proportional to the shunt field current, then if the load changes, the interpole compensation is same, but I should modify my compensation according to the load current, right? According to the armature reaction, and armature reaction is proportional to the load current. That's why the field current is proportional to the armature current. Hence, the mmf of interpole will be proportional to the armature current. That is the advantage. So these are the key points. You can go through and read over this. One more important point is number of interpoles will be equal to the number of main poles. So in this case, I had 2 poles, main poles, hence I will have 2 interpoles. If I had 4 main poles, I will have 4 interpoles. Okay. Also, air gap under interpoles is deliberately kept large to prevent saturation. So because they are very narrow, right? Because they are very narrow, the flux density will be very high, because they are very narrow, as they are as interpoles are very narrow, flux density will be very high. Now, if flux density is very high, that means what? That means saturation can happen. To prevent that, what we do? We make the air gap to be higher to reduce the flux density, to reduce the overall flux. Okay, because reluctance will be higher then. So that's why we keep the air gap higher. Air gap is more higher, so that flux like core does not get saturated. Okay, so this was one of the way in which we can actually what do you do? We can actually reduce armature reaction. What is the other way in which we can reduce the armature reaction? So what we can do is, we know that if I have current carrying conductors in a field, like they will generate, for a generator, I'm drawing the direction of flux for a generator. The flux generated will be something like this, right? And it will pass on through the field poles as well. So what I can do is, I can see this flux, right? Flux path. I can try to increase the reluctance of this flux path so that the flux is lower. Correct? So what my aim is, because I want to reduce the armature reaction. How can the armature reaction be reduced? This flux mmf has to be reduced. How can I reduce it? If I can somehow make a high reluctance path for this flux, right, then the armature flux will reduce. So I want to reduce the armature flux. So how do I do it? So how do I do it? What I will do is, I will increase the reluctance of flux path. Okay, so how can I increase? So this field poles, right, are very good for flux to pass. So what I can do, we can punch holes here so that the reluctance of this path is higher, so that the flux is lower. So we can either we can do field pole laminations, that also can make the reluctance higher. Also along with that we can do rectangular punched hole, which can increase the reluctance so that armature reaction is significantly reduced than the main field flow fold flux. Okay, than the main field fold flux. Okay, sorry, field pole flux. Okay, yeah. So uh, one more thing, let's discuss about the nature of armature reaction at the pole tips. Okay, what is the nature of armature reaction at the pole tips? So what do I know? If I just go back, right, if I go back, we actually summarize one thing, right, about armature reaction about the pole tips. I guess if you remember, where is it? Here. So this was the summary, right? I'll just quickly copy this. Quickly copy. Okay, this one they will not let me copy. So what we summarized was that the effect of armature reaction is the MNA will shift, whatever, I don't care. The flux will increase under the trailing pole tip for a generator. So if my generator is rotating like this, what is the trailing pole tip? Trailing pole tip will be the this one, right? And leading pole tip will be this one. So flux will increase in the trailing pole tip and flux will reduce in the leading pole tip. So what we can do is we can, at leading pole tip the armature adds the flux, so flux, yeah, increases, right? Sorry, for a motor, is it talking about motor? Okay, this should talk about a motor. Okay, this is for the motor. Okay, they are talking about this is for the motor, and for a generator it will be just the opposite. Okay, for a this is for a motor. For a generator it will be just the opposite. Okay, so let's discuss for motor only. So I know at leading pole, so at leading pole tips the flux increases, right? For a motor it will be just the opposite. So flux increases at the leading pole tips. What I can do, I can increase the reluctance around the pole tips. So if I increase around both the, if I increase the reluctance of both the pole tips, what will happen? Because there is huge increase in the pole here, right? Huge increase in the uh, like in one of the pole tips there is huge increase of flux lines, in the other pole tip there is not that much increase in the flux lines. But I already have told you that one of the pole tips can go to saturation. So if one of the pole tips can go to saturation, so increase is 4. Like if let's say total I have 8 flux lines, so at the top I will have 4 flux lines, in the bottom I will have 3 flux lines, right? If I assume that although it should have been 5 flux lines in the top, but due to saturation I can only support 4 flux lines, and here in the bottom I have 3 flux lines. So what I can do, I can further provide reluctance on the both the edges, so that what happens, where the flux lines are lower it will not affect the MMF much, but where the flux lines are very high it will try to go back and go back to this number of flux lines. So basically there will be balance. Basically this will not, this shift will not happen, shifting will not happen. What will happen, the direction of the flux will be somewhat like this, because on my main purpose is to make the flux lines similar on both the pole tips, both the trailing and the leading. Okay, so what we do, so we try to, we increase the reluctance. Why? To make make the voltage, make the flux lines similar on both the pole tips. So that was it. Basically, how we can achieve it? So we can do it by chamfering of poles. This we had already discussed, right? Chamfering of poles initially. But that time I did not tell you that that time it seemed like chamfering of poles is waste because we want to keep the air gap uniform, right? But now it seems like chamfering of pole is good. So it all depends. There is a balance between what we want to do and what we don't want to do. So it all depends. Okay, whether we want to chamfer or we want to keep the air gap same. Okay, and other ways are there. Laminating, punching holes. This we already had discussed. Okay, so this is it. How we can chamfer the pole. So near the center, the air gap will be minimum, and near here the air gap will be maximum, so that the flux is purely sinusoidal. So here the main field flux will be almost stable. MNA will not totally move, right? MNA will not shift because the main field flux will be still in this direction. Main field flux will be still in this direction. Okay, I hope you have got this point. So yeah, these are the few things that we must understand. Now let's discuss about compensating winding. Okay, let us now discuss about compensating winding. What is compensating winding, right? So compensating winding is nothing, the same thing only, but now in the main this is the main pole. In the main pole I will connect few conductors like this. Okay, and what's the purpose of these conductors? The purpose of these conductors is to produce a magnetic flux that will oppose the armature reaction. So this direction, this is the main field, right? Main pole. So this is the d axis. Basically this will be the d axis. Okay, so this is the d, so I can copy from here only, right? Copy from here. This will be the q axis, this will be the q axis, right? So what I can do, okay, let me okay, this q, okay. So what is happening is that like another thing, compensating winding again is connected in series with the armature. So again, if I just write down, if I just draw the mmf produced by the compensating winding. Okay, what is the mmf produced by the compensating winding, right? So if you see, mmf is what? mmf is h dot dl, right, which is equals to I enclosed, correct? So if I just take this portion into isolation, only one negative current is there, right? Or it is the if I assume negative to be if I assume that this dot to be the positive value, if I assume, I have to assume a direction, so I am assuming dot to be positive. Okay, and initially I am at here the lowest point. Okay, So here I am at the lowest point, and as I am encountering the currents, what is happening? I enclosed is increasing, so the mmf also will increase. It will increase. It will provide 0 mmf and in the d axis, right? From negative, it will provide 0 mmf in the d axis, and it will provide highest mmf on the q axis, both in the positive and negative direction. So that is what we want actually, because again, what is our main purpose? Our main purpose is to reduce the flux in the pole tips. We don't want to do anything in the d axis. Okay, so that's why our main purpose is to reduce the what do you say, reduce the mmf on the q axis that has been formed due to the armature reaction, right? So this compensating winding will do the same thing. So this is the mmf provided by the compensating winding. Okay, and also again the same thing, right? Same like interpoles, compensating winding will be connected in series with armature, right? So here the current, field current, will be basically the armature current, okay, of the I compensating will be the armature current. Okay, so that's basically about the compensating winding. We can use both of these to together like remove the armature winding. So here, right, if I use interpoles and the compensating winding, so compensating will be something like this, right? It will oppose the armature flux. It will just be the opposite of armature flux. Okay, like definition of compensating winding is that we will connect the compensating winding as to cancel the armature reaction. So we will connect the compensating winding such that we will wound the compensating winding such that it opposes the armature flux. So if the armature flux is negative, it will be positive. Just it will oppose the armature flux, right, in the pole tips, because in the q axis we are using interpoles to reduce the armature reaction, but we have to reduce the armature reaction in other places as well. To reduce the armature reaction in other places, what we'll do, we will use compensating winding. So this will totally nullify the armature reaction. Okay, so roughly the shape of the, if you measure the roughly the shape of the resultant magnetic flux, right, will be somewhat like this. Okay, it will be again similar to the field flux roughly. Okay, so again, like this is our main, this is what we wanted, right? This is what we wanted. So roughly our resultant flux density will be flat top. This is what we initially derive all the expression for. So we will get back our final expression if we use compensating winding and interpoles together, right? Because interpoles will cancel out the flux in the q axis, compensating winding will cancel out the flux in the what do you say, along the pole tips. Okay, so now let's discuss that. So this is the theory about compensating winding, need for compensating winding. Even after using interpoles, armature reaction under the pole faces can severely distort the main field, especially at heavy loads, because if the armature current is higher, more field flux will be there. Thus what we do, we use um, uh, this causes peak flux density variations under poles, increased risk of high localized EMF, and commutator flashovers can happen. Okay, so compensating windings are designed to cancel the armature reaction under the pole faces. They are placed in slots. So in the slots of the, what we do is we make slots of the pole shoes, right? We make slots out of the pole shoes, and in those slots we place the compensating winding. Okay, field windings are placed here, compensating windings are placed here just to cancel out the armature reaction on the pole faces. Okay, and in the q axis interpoles will be present. In the q axis interpoles will be present. Okay, so that's the complete picture. I hope you get the complete picture now, how compensating winding is placed, how and how it actually cancels out. Okay, so again the same thing, right, that we want to derive is that here, right, current in compensating winding is made to oppose the armature current locally. Like basically we will connect our armature winding such that it will oppose, it will make a flux, it will also generate a flux such that it opposes this conductor. Okay, so flux density produced by the compensating winding is opposite to the armature. Thus, the armature flux under pole arc is nullified, keeping that net field distribution uniform and avoiding peak flux density will shift. So, peak flux density will be again similar, so it will be flat topped. Okay. So, now same thing is written over here, that compensating winding, these are embedded in the pole faces. They carry armature current. Current is directed such that it will oppose the flux. They will cancel the direct axis component of the armature reaction. Q axis is already cancelled by the interpoles. Okay, so interpoles are used for Q axis, compensating winding are used for the D axis. So interpoles will mainly help in commutation, because in the Q axis commutation happens, right, and reactance voltage will be generated that time. So in the Q axis commutation happens, which we will discuss in the next lecture. So that's why interpoles mainly help in the Q axis, and compensating winding mainly helps in the D axis. Okay, placement will be between the main poles in the interpolar axis. Okay, between the main poles, and in case of compensating winding, it will be in pole faces. Again, it is connected in series with armature. Both interpoles and compensating winding both are connected in series with armature. Application used in most DC machines. Okay, and these are mostly used in large high current machines. Okay, mostly both of them together will be used actually. So now let's discuss about the like numericals, from where the numericals will come, right? Mainly we are studying for gate, so in gate numericals will come. Okay, theoretical portion we have already covered. Okay, so numerically let's derive few values through which we will be able to answer the questions, right? So my interpoles are here, my compensating windings are here. One more thing I have already discussed, that total armature current is IA. So what is the current per path? That is current per coil. How much current is there in per coil? It is IA divided by A. That is the current per path. Total number of conductors is Z, right? Total number of conductors is Z. What is the total number of turns? So I know one turn have two conductors, right? So if I know the total number of conductors, how many turns I will have? Z by 2. So total number of turns will be Z by 2. Okay, total number of turns is Z by 2. Got it? Now let's discuss our formulas. So first one is, what is the total MMF produced by armature conductors? What is the total MMF produced by armature conductors? It should be the total number of turns, that is Z by 2. So this already we have discussed in the previous lecture. Z by 2 N of total number of conductors of the, sorry, number of turns of the overall armature, that is Z by 2, into the current per coil or current per conductor. What is the current per conductor? It is IA divided by capital A. NA is Z by 2. So Z by 2 into IA divided by capital A. This we had already previously derived as well, right? Previous lecture also we have derived this. Now, what is the per pole MMF generated? Because of course I will connect my interpoles each pole, right? So I want to calculate the per pole MMF generated. Per pole MMF generated will be just all of this divided by P. So if we see here, all of this if I divide by P, this will be the ampere turns per pole by the armature. Okay, so ultimately this value I have to nullify, right? This is the extra value, this is the extra ampere turns that is getting developed that I don't want. So this I have to nullify ultimately. Okay, this is the key point. Now, this also corresponds to the peak of the triangular waveform representing the armature MMF distribution. So this value is also equals to the peak, right? If you remember, the armature mmf was something like this, right? So this value is the peak. This whatever we have derived, this value is the peak. Okay, peak value. Because at max this can be the maximum mmf that can the armature can actually produce. So if I can nullify the maximum mmf, then ultimately armature reaction will be nullified. Okay, so that's done. Now how will I nullify this? How will I nullify this? So I can nullify this with compensating winding. So if I connect the compensating windings here, what is the ampere turns by the compensating winding? So uh, what will be the total number of turns, ampere turns provided by the compensating winding? That is what we want to find out, right? So actually, if I assume the number of turns of the compensating winding to be the same as the armature, okay, then how much mmf will overall my compensating winding be like cancel out, nullify the mmf? It will be basically because it is not covering the whole 90 degrees, right? Whole 180 degrees mechanical. It is only covering this much, right? So basically we will use the same formula, that ampere turns, not this. So total ampere turns per pole of compensating winding will be this value, whatever we have calculated, that is Z by 2p, Z by 2p into Ia by A into the pole arc upon pole pitch, because I am not covering the whole poles here, right? Not covering the whole poles. Now remember, this is just assumption that my number of turns of the compensating winding is same. If I assume that the number of turns of the compensating winding is NC, right? If I assume the number of turns of the compensating winding is NC, then it will be NC into Ia divided by capital A into pole arc upon pole pitch. Now from here you can easily find out what is the value, how many number of turns I need to connect in the compensating winding, so that I can cancel out my the armature mmf. So I will equate this value with this value, and from here I will be able to find out my NC, right? This Na will be Z by 2. So from here I can easily find out my NC. Okay, one way to find out. Now because this is the total ampere turns per pole, now what is that I want to, okay, this is the, okay, I already, okay, this is the total turns only. Okay, we have already calculated this only. We don't need to write this. This is extra. So okay, what is the total conductors per pole? So how do I calculate the total conductors per pole? Total conductors per pole will be just Zc divided by 2, right? Nc will be equals to Zc divided by 2, because each turn will have 2 conductors, correct? Each turn will have 2 conductors. So this will be, oh sorry, yeah, each turn will have 2 conductors, so it will not be Nc divided by 2, sorry. Each turn has 2 conductors. Let's say if I have 1 turn, I have 2 conductors. If I have 10 turns, I will have 20 conductors. So if I have Nc number of turns, so total conductors per pole of the compensating winding will be 2 into Nc, right? This many 2 into Nc, okay, divided by P also has to be there, because 2 Nc will be the overall number of turns, divided by P also will be there. Okay, this will be the total number of conductors per pole I will require, because Nc will be the total number of conductors. So Nc is what? Nc is the total number of conductors. Total number of, not conductors, sorry, total number of turns of compensating winding. Compensating winding. Okay, so per pole number of turns will be 2 Nc divided by P. Got it? Very well. Now let's discuss about the interpoles. So if no armature, no compensating winding is connected, I know what does the interpoles has to nullify. The interpoles has to nullify this ampere turns, right? Peak value of this flux, and the flux density here. So Bi is the magnetic flux density between the interpoles that the interpole has to nullify. So interpole has to nullify this ampere turns as well, also this whatever flux is getting generated. That is why the interpoles are connected, right? So the without compensating winding, if no compensating winding is connected, so without compensating winding, the ampere turns of the interpole or the ampere turns per pole required for interpole will be what? It will be basically the Z by 2 P into IA divided by capital A into this was the ampere turns of the this was the ampere turns of the armature reaction. Along with this, additional flux it needs to generate so that it can nullify this flux, right, on along the q axis. So they will give you in the question, don't worry, what is the additional flux, right? It will be Bi. So how do I calculate the ampere turns? I know H dot L equals to my Ni, right? What is H? H is basically what is B? B is basically mu H, right? Or I can write H is equals to B by mu, correct? So here this will be B dot L divided by mu. Okay, so I will, so ultimately, right, H dot L is the MMF that I need to oppose. So H is BL divided by mu. L is the basically the air gap length. B is the flux density and mu is the mu naught. It is air gap, so it will be mu naught only. So this will be Bi Li Lgi divided by mu naught. Okay. Now if compensating windings are present, so already I am compensating, right? Already I am compensating. So that one I will not nullify, right? So interpoles are there to nullify the ampere turns of the armature and also this q axis flux, right? But if already I am nullifying using the compensating winding, whatever I am nullifying that I will write here, right? So whatever I am nullifying, this I will write. So this overall ampere turns will be with compensating winding. Overall I had this much amount of ampere turns in the armature reaction. Bit of it I am nullifying with the help of compensating winding. So I will subtract this value. Whatever is the number of turns of the compensating winding, I will write over here. Okay. So this will be minus and this will be again plus of whatever the flux is there, that again anyways the interpole will only nullify. So this, right, this is the additional MMF that interpole needs to nullify after the compensating winding has nullified bit of it, right? Compensating winding, let's say, has not nullified this whole ampere turns, bit of it is left. So plus whatever this flux is there, this will stay because compensating winding anyways does not nullify any flux in the q axis, right? It does not nullify. So understand conceptually what is happening, don't just mug up the formulas. Okay, so we have understood whatever is happening conceptually, everything whatever is happening, everything conceptually. Okay, so I hope it is clear. So now let's do bit of numericals to understand whatever we have learned. Okay, so let's do this first question. Which one of the following statements about armature reaction MMF in a DC machine are true? It remains stationary with respect to the main field poles. Armature reaction MMF, does it remain stationary with respect to the main field poles? No. It remains stationary. Which of the following statements about armature reaction in DC machine are true? Armature reaction MMF are true. It remains stationary with respect to main field poles. It rotates relative to the field poles. It rotates relative to the armature. So armature reaction, okay, one thing, armature reaction, does it, so if I have armature reaction, right, so this is the effect of armature reaction. If I show you, where did it go? Here, this is the effect, another effect, yeah, here. So if we see here armature reaction, right, one thing I notice that for the main field flux, right, the field lines will just change their direction with respect to the main field flux, right? So with respect to the main field flux or with respect to the main field poles, it is stationary. So it remains stationary with respect to the main field poles, because I see the effect of the armature reaction, what happens, it is always in the q axis, right? Always in the q axis, right? So with respect to the main field poles, it will remain stationary. With respect to the, it rotates relative to the field poles, no. It rotates relative to the armature, yes. So if I have a conductor here and the field flux will rotate relative to the armature conductors. Yes, but if armature itself is rotating, okay, what is happening? Overall, the armature flux is in the q axis only. It is stationary with respect to the main field poles. So option 1 and 3 will be correct here. So option C will be the correct answer. So this is kind of a trick question. Okay, ultimately your armature reaction flux, right, is always in the q axis, and q axis is always stationary with respect to the main field flux. But as armature is rotating, armature is changing its direction, around it the flux is rotating, right? So relative to the armature the flux is rotates, but relative to the main field poles the flux is stationary. Okay, very key point, important point to understand. Let's read this next question. Which of the following statements about interpoles in DC machines are correct? Which of the following statements about interpoles in DC machines are correct? They help minimize the effects of armature reaction in the interpolar zone. Yes, it is correct. They will help in minimizing the armature reaction in the interpolar zone. Let's read the second statement. Their windings are connected in series with the armature. Yes, they are connected in series with the armature. This is again correct. They have very small dimension as that of the main poles. Yes, this is also correct. They have a very small dimension as that of the main poles. Again, this is also correct. So yeah, both 1, 2, 3, all of them will be correct in this case. Now let's solve the next question. So next question is here. So a 440 volt, okay, I will keep on writing the values. 440 volts. So terminal voltage V is 440, poles is 4, it is 25 kilowatt, power rating is 25 kilowatt. It is a DC generator, wave wounded. So number of parallel paths will be 2. Armature with 846 conductors. So conductors are 846. At full load, the main flux density in the interpolar region B I, right, in the interpolar region is 0.5 Weber per meter square, and the radial air gap, that is LGI, is given as 0.3 centimeter. Okay, so how many turns are needed to each interpole, in each interpole? So basically turns per interpole they are asking, right? So what is the total flux that I need to compensate here? What is the total mmf that I need to compensate? So total mmf that I will need to compensate will be equals to whatever is the mmf due to the armature reaction, that is Z upon 2p into Ia by capital A, plus the interpolar region mmf, because there are no compensating windings. So overall I have to compensate the ampere turns due to the armature reaction plus the interpolar region q axis, right, that is also due to the armature reaction only. So this is equals to Bi divided by mu naught into into Lgi, right? Yeah, okay. So from here I can directly find out the values. So do I even need this 440 volts? I guess I don't need. Okay, armature current they have told me. What is the okay, I need basically they have not told me full load. So my machine is rated at 25 kilowatt at the output. So the rated current IA will be 20 kilowatt power by voltage. Although roughly it will be approximately, because there will be some drop in the armature resistance. They have not mentioned the armature resistance, so I will approximate it. So roughly it will be equal. Okay, roughly my IL rated will be roughly equals to the armature current rated. Okay, so this will be 25 into 10 cube divided by 440. So from here I can find out the armature current value. This will be 25,000 divided by 440. So 56.81 will be the rated current in this case. Okay, 56.81. 56.81 amperes. So I will replace all the values over here. So my Z will be 860, 846. It is a 2-pole machine. It is a 4-pole machine into armature current, that is 56.81, divided by the number of parallel paths, that is 2, plus bi is 0.5, divided by mu naught, that is 4 pi into 10 raised to power minus 7 into 0.3 into 10 raised to power minus 2. Okay, so this will be equals to, I can find out the values here. So 56.81 divided by 2 into 846 divided by 8, okay, this will be 3004. And remember, it is connected, so they are asking me the number of turns, they are asking me the number of turns, right? So it will be interpole turns, the mmf will be interpole into the armature current, ia will be there, right? So ia anyways will be cancelled out later on. So this will be 3004 plus 0. What is this value? This is 3004.26. 0.26. So this value will be 0.5 divided by 0.5 divided by 4 into pi into 0.3 into 10 raised to power 5, 10 raised to power 5. So this is 1193.66. Okay, so this plus 3004.26, this roughly comes out to be 4197.92, and n interpole will be this divided by the number of by the current 56.81, because it is connected in series, so that's why the current is same. Roughly it comes out to be 73.89. Of course it will be a integer number, so roughly it will be 74. So 74 turns will be answered per pole. No, this is not per pole, right? This is the overall. Okay, this is the overall number of turns, correct? Yeah, overall number of turns. So turns, they are asking per pole. So per pole turns will be what? This divided by the number of poles, interpoles. How many number of interpoles I have? 4. So this is the total turns, correct? So n interpole per pole will be 74 divided by number of poles, that is 4. So if I divide this by 4, this roughly will come out to be 19. Okay, so 19 here will be the answer, because this n interpole into ia was the total mmf. I had not calculated here per pole, right? I had not divided by per pole. This is the total mmf. Sorry, this is the per pole mmf, right? Sorry, this, right? Sorry, one more thing I missed here. This should be divided by p as well, right? Because I have to find out the per pole mmf. This is the per pole mmf on the right hand side. Left hand side also will be per pole mmf. Sorry, I messed up. Sorry. So roughly, right, what is happening? This multiplied by p will be the total number of turns. This value will come out to be roughly 295.576. So turns per pole will be what? This total number of turns, because this is the total number of turns that I have calculated, divided by the number of poles, so that is 4. So roughly it will come out to be 74. So 74 will be the answer. Okay, 74 will be the actually answer, because here, right, I forgot to divide by the number of poles, because here the right hand side is what? Right hand side is ampere turns per pole, right? Because this, whatever ampere turns you have calculated, this is only under a single pole, right? Same for here, only under a single pole. So same should be on the left hand side as well. Okay, now let's discuss this question 31. A compensated DC generator has 12,000 armature ampere turns. Okay, so it has 12,000, compensated DC has 12,000 ampere turns per pole. So ampere turns per pole of armature. will be equals to 12,000. Okay, given that the pole arc to pole pitch ratio is 0.7, so pole arc to pole pitch is 0.7, the length of the interpolar air gap LGI is 1.25 centimeter, flux density of the interpolar region BGI is 0.3 Tesla. Determine the required ampere turns per pole for the compensating winding and the interpole. Okay, so if I am using both compensating winding and interpoles, what I will do, interpole will be there to remove this, right, the flux density along the q axis along the interpolar region, and the compensating winding will be used to reduce this ampere turns. So how much compensating ampere turns I will require per pole? It will be equals to what? Because whatever ampere turns the compensating winding will produce, I have to multiply that with 0.7, right? Because it will only cover 0.7 of the portion, correct? 0.7 of the portion. Am I correct? Compensating has this much amount of ampere turns. Given that the pole arc to pole pitch is this, the length of the interpolar region is this. How much? Okay. Okay, sorry. Okay, this is the overall ampere turns of the armature. Okay. So how much will the compensating winding will cover? A compensated DC generator, okay, it is already compensated. A compensated DC generator has 12,000 ampere turns per pole. Okay, the pole arc to pole pitch is this, the length of the interpolar air gap is this. Determine the required ampere turns per pole for the compensating winding and interpole winding. So it is a compensated DC generator, already it is compensated, so overall compensation is 12,000. Okay, so out of the 12,000, how much will the compensating winding cancel out, nullify? That is what they are asking. Actually the question is not properly framed. So compensating winding, right, compensating winding ampere turns will cover basically only the 70% of the pole region, other 30% will be empty, right? So this will be equals to the overall ampere turns per pole into 0.7, right? That will give me the per pole ampere turns of compensating winding, because compensating winding only cover 0.7 portion, 0.7, like 70% of the pole pitch, correct? That's why. So this will be 12,000 into 0.7, so this will come out to be 8400. Now how much will the interpole winding compensate, right? So interpole winding will compensate this rest of the ampere turns, whatever is left. So interpole winding, right, interpole winding ampere turns per pole will be basically this 12,000 minus the 8,400, whatever the compensating winding has compensated, plus the interpolar region. So it will be BGI into BI into LGI divided by the mu naught. So this will be basically 3,600 plus BGI. BGI is given as 0.3. LGI is given as 1.25 centimeter into 10 raised to power minus 2 divided by mu naught. So mu naught will be 4 pi into 10 raised to power minus 7. So this will be 0.3 into 1.25 divided by 4 into pi into 10 raised to power 5. 10 raised to power 5 plus 3600. So roughly it will be 6584. 6584.115. Okay, this will be the amount of ampere turns that the interpole will have to compensate, because compensating winding will only compensate 70% of this, right? The rest will be compensated by the interpole. Okay, so let's discuss few theoretical questions. What happens if the brushes are shifted opposite to the direction of generator of rotation, or in the same direction of rotation of the motor? So if I move the brush, what is happening? What we remember, I remember very one specific thing, that in case of a generator, the MNA will shift in the direction of rotation of generator, and it will shift in the opposite of the direction of rotation of the motor. So this you have to remember, unfortunately, or you can derive at the exam hall as well. So for generate like MNA shifts for generator in the direction of rotation, and for motor opposite to the direction of rotation. Correct? So here what we are doing, we are actually doing the opposite, right? We are, what happens, what we are doing, we are doing the opposite. So we are shifting opposite to the direction of the generator, and in the direction of the motor we are doing opposite. So we are not going in the direction of the MNA, we are going, hence in the question we are going in opposite direction of MNA. And if we are going, if the MNA is shifting, right, if we are going, moving our brushes in the opposite direction of the MNA, that means what? That means there will be commutation problem. We will see what kind of problem in the next lecture. Commutation problem. There will be sparking. Okay, all these problems will be there. Okay, if I move further away from the MNA, so there will be sparking commutation problem. So this is the answer basically. Okay, what will happen? Sparking will happen. In a series circuit, the interpole is connected what? In series with the armature, in parallel with the armature, in series parallel with the armature. So it does not matter. It will be connected in series only. Interpoles are always connected in series with the armature. What impact does the armature flux have on the main field flux? So it has both cross magnetizing and demagnetizing. Correct? Cross magnetizing, basically it is 90-degree perpendicular to the armature flux along the q axis. In the q axis, right, it is cross magnetizing, and in the d axis sometimes it is demagnetizing. It is directly opposing to the armature flux, opposing to the main field flux. Okay, so option C will be the correct answer. In DC machine, the demagnetizing component of the armature reaction arises due to what? So basically, I know you have a bit of doubt that how demagnetizing happens, right? So if I show you that this thing, previously, if you remember, where is the picture? It is here. Yeah, here is the picture, right? So I'll copy this and I will take it. So how does demagnetizing happen? So q axis, cross magnetizing flux is there. So along the q axis, I know that q axis is the cross magnetizing flux basically. So I'll copy this here as well, because I think this would not have been cleared. Just give me 1 second. Give me 1 second. Yeah, so I think this would have not been cleared here. So if you remember that cross magnetizing meaning overall flux, right? Overall flux. So if I copy this again, overall armature flux would be something like this. Correct? It will be something like this. It will be something like this down. So and main field flux will be in this direction, right? Main field flux will be in this direction. So it is in cross direction, basically in the q axis 90 degrees. So whichever one is in the 90 degrees, that is known as the cross magnetizing flux. So we have cross magnetizing flux for armature reaction. What is the demagnetizing flux? So demagnetizing basically happens in the pole phases. Why? Because in one of the pole phases there is like 4 flux lines. In the other pole phase there will be 3 flux lines. There will not be 4. Why? Because here flux lines got reduced. It tried to go to the other pole phase due to armature reaction, but due to saturation it could not increase the number of flux lines. So it remained on 4, already discussed. So this is the demagnetizing effect due to armature reaction. So both demagnetizing and cross magnetizing effects are there. Same here as well. Okay. So in DC machine, the demagnetizing component of the armature reaction arises due to the magnetic saturation over 1/2 of the pole area. So as there is magnetic saturation, so my strengthening of flux, right, will be lower. So if let's say I had 4 flux lines on the top and the bottom, So the top flux lines will not increase due to saturation, but the bottom will decrease. So there is more weakening than strengthening. So strengthening, what is the spelling of strengthening? I have forgotten. Strengthening is less than weakening. As strengthening is less than weakening, what will happen? As strengthening is less than weakening, okay, weakening, basically I can say that the, what I can say, I can say that there will be uh, demagnetizing of the main field flux. Main field flux will reduce. Main field flux will reduce. So basically, right, flux will reduce. So basically this cross magnetizing flux actually does not reduce the mean, like overall magnitude of the main field flux. It just changes the direction of the main field flux. So this I think I have not defined you what is cross magnetizing and demagnetizing. So basically I will define it here only. So cross magnetizing is the flux that changes the direction, because the main field flux is in this direction and cross magnetizing will be in this direction. So cross magnetizing will change direction of main field flux, and basically demagnetizing will weaken the main field flux. So demagnetizing, right, demagnetizing will be in this along anti-parallel to the main field flux. So if the main field flux is here, so demagnetizing will be here. So here this will be the demagnetizing flux, Fa demagnetizing, and this is the, like if the main field flux is here, the cross magnetizing will be here or here, that is Fa cross. Okay, so I hope this basic distinction is clearer to you. So let's do more theoretical questions. So why interpoles are used in DC machines to neutralize the reactance voltage? Kind of yes, because we improve the commutation at the we improve the flux at q axis, right, is change. So at q axis what is present? Brushes are present. So what does brushes do? Help in commutation, right? So if I don't nullify the q axis flux, then there will be reactance voltage, there will be sparking, right? So that's why the interpoles mainly help in the neutralizing the reactance voltage. The demagnetizing effect of armature mmf is uh, mainly counteracted by the compensating winding. So interpoles mainly help in the commutation, and commutation basically means it mainly nullifies the cross magnetizing armature reaction. So it will mainly nullify the cross magnetizing armature mmf. Okay, so I hope you have understood. So mainly interpoles help in the reactance voltage and the cross magnetizing armature mmf, and your and your compensating windings will mainly help in the removing the demagnetizing armature reaction. Okay, so same thing, same question here. So what is the answer? Answer is option A. So in DC machine, which of the following statements is correct? Compensating winding neutralizes armature reaction while interpole generates residual flux. Compensating winding neutralizes armature reaction and interpole winding improves commutation. Okay. Compensating winding improves commutation while interpole windings neutralize armature reaction. Compensating winding improves commutation. Okay, only option B will be correct, right? Because compensating winding is used to neutralize the armature reaction. Interpoles also neutralize the armature reaction, but mainly it is used to nullify the magnetic flux along the q axis that is used to improve the commutation. Okay, so that was the answer over here. Like these are all mostly theoretical questions. Let me move on to the next question. In DC machine, the compensating winding is placed in the armature slots to counteract. No, it is not placed in the armature slots. Mounted on the commutating poles to enhance. Positioned on the pole shoes to prevent flashover at the commutator. Located at the pole shoes to minimize sparking at the brushes. No, this right. These are located at the pole shoes to minimize the sparking at the brushes. This is for the interpoles, right? Yes, compensating winding are located in the pole shoots, but they are okay in the field poles. Actually, they are mounted on the field poles only, placed in the armature slots. So out of this, right, actually this is also totally not correct. They are actually placed in the like field poles, but here out of all the four options, only option C will be correct, because of course compensating winding is not placed in the armature slots. Of course, they are not placed in the armature slots. They are not placed mounted on the commutating poles. No, nothing like that. So out of this, option C will be the correct answer, right? So let's now solve this next question. Okay, so this is the next question that we want to solve. A long shunt generator equipped with interpoles is commutatively compounded. So it is commutatively compounded. That means what? That means my overall flux, right, field flux, will be aided by the shunt flux plus the series flux. Okay, commutatively compounded. Okay, it is a long shunt generator. It is a DC generator. Okay, without changing the supply terminals, the same machine is now operated as compound motor. So previously, if I draw my generator, so this is my generator, this is a motor, okay, and this is a generator. Yeah, this is a generator. Okay, this is a generator. Okay, so what I can say is, if I don't change the supply terminals and I work it as a motor, what will happen? Then the current direction will change. Previously the current direction was here, now the current direction has changed, correct? So armature current direction IA dash will be minus of IA. Okay, that is one thing, right? So if IA dash is minus of IA, then what they are discussing, we will discuss about that. So now as operated as a compound motor, assuming that the shunt field is stronger than the series field, okay, will the motor operate as cumulatively compounded or differentially compounded? Okay, that is what they are asking. So if you observe, previously it was working in commutatively compounded, that is both the flux were aiding each other, both were in the same direction, the series field and the shunt field. Now as soon as I change the direction of the current, the direction of the mmf generated by the series field will be changed, right? It will be opposite. Okay, but this direction remains same, right? Because here also the current direction is downward, here also the current direction will be downward, because mainly is will supply now the ia and the ish, and previously ia was supplying ish and is, right? So what they're telling me, that the shunt field is stronger, so shunt field is stronger. So now actually if I see, now the field flux, right, overall field flux, my it is phi sh, as it is stronger, I will write this one first, minus phi se. So actually it is operating as a differentially compounded machine. So it operates as a differentially compounded machine. So for the first question, it will operate as differentially compounded machine. Okay. Do the interpoles retain the correct polarity to ensure proper commutation in the motor operation? Now, will the interpoles retain the correct polarity? That is what we want to know. So, for that, right, we have to understand what is the direction of the rotation, right? What is the direction of the rotation that we have to understand? Okay. So, for that, I can I can take out this diagram. What is that diagram? Where is it? With the interpoles one. Okay, it is not here, yeah, here. So, if let's say the initial torque was in this direction, this was the initial torque direction, that is where the generator is rotating. Now, if I like, due to that, my supply voltage was coming like this, right? It was plus minus V. Now I am not changing the supply voltage here, but the armature current direction previously was on the right hand side. Now it has changed to the left hand side. So it is incoming, right? So let's understand with the proper equation, right? So previously, what is the equation? Previously, let's say if my for in case of generator, in the case A, in case of generator, so it will be basically what I can do, what I know is that it is equals to omega g into the torque that I will give to the generator will be equals to the Eg into Ia, right? In case of motor, what is happening? In case of motor, it will be equals to omega motor into torque of the motor equals to Eg into Ia, or Eb into Ia dash, right? Or I can write what is the, like, basically what is the direction of the torque. So let me not compare like this, sorry, no, let me not compare it like this. I can directly compare the torque. So torque of the generator will be proportional to the flux, right? Flux of the field into the armature current. So here as well. So what is the flux of the field? Previously the flux of the field was phi sh plus phi se, and Ia was Ia only. Okay. Now in the second case, torque of the motor, because I want to understand what will be the direction of the rotation. So in the second case, what I can say, torque of the motor will be phi f again into Ia dash, right? Phi f dash into I dash. So what is phi f dash? Phi f dash now has changed. It is phi sh minus phi ac. But again, as the shunt field is dominating, so phi f also will be in the same sign. So let me take few examples. Let's assume that this is 1 Weber. So this is, let's say, 2 Weber, and this is 1 Weber, right? Phi sh is more than phi se. So here also, if I see, this will be 2 minus 1, still 1 Weber, still in the same direction. Previously, what was the direction? 3 Weber, right? Same positive. Now also it is positive. So sign of the flux does not change. So flux is still positive. So phi f dash, phi f is positive. If I assume phi f to be positive, then my phi f dash also will be positive. Okay. What about Ia? Ia direction has changed, right? Because the current direction previously it was outgoing from the generator, now it is incoming. Okay. So previously it was outgoing from the generator, now it is incoming, right? So Ia dash is negative, that I have already mentioned here. Ia dash is negative. So if Ia dash is negative, that means Ia dash will be, if Ia is assumed to be positive, then my Ia dash will be negative. That means what? That means my torque develop will be negative. That means my motor will be rotating in the left hand side. So all this is fine. So all these are fine. So motor will be rotating in the opposite direction. So that is already drawn over here. So what are they asking? What are they asking? They are asking, do the interpoles retain the correct polarity? Yes. As here, right? Previously I derived that if generator rotates in the right hand side, then the interpole polarity should be the leading pole, that is S. Okay. For motor it is the opposite. If the motor is rotating here, so the leading pole is north, then the interpole should be opposite, south. So I don't need to change the interpolar axis. So interpolar axis is already in the correct polarity. So the answer to the option 2 is interpolar axis. So that's why we don't need to change the interpoles every time if I use it as a motor or generator. So interpolar axis will remain same. Okay, will be in correct polarity. Okay, interpolar axis will be in the correct polarity. Okay, now what is the third? Will the direction of the rotation remain same as it was during the generator? No, no, right? This we have already discussed. The direction of rotation will change. Direction of rotation will change. Okay, direction of rotation will change basically. So whatever we have discussed, same thing is written over here. You can go through it. So it will be no and here. So whatever we have discussed, you can go through here. You can read this. Okay, so let's now solve this question. So here what have they asked? They've given us that we have a 4 pole, P is 4, 100 kilowatt. So power is 100 kilowatt. This is the power rated. Voltage is 200 volts. It is a lap bonded. If it is lap bonded, that means the number of parallel paths will be equal to the number of poles. Has okay, what is the number of poles? 4. It has 256 conductors. 256 conductors. If the interpolar air gap is 1 centimeter, interpolar air gap is 1 centimeter, and the flux density under the poles Bt is 0.25 Tesla. Determine the number of turns required in each interpole. Same thing, right? So number of turns required in each interpoles. So I have to nullify the armature MMF plus the additional, because here they have not mentioned any compensating winding. So interpoles has to nullify everything. So the ampere turns, determine the number of turns. So ampere turns per pole by the interpole will be equals to the ampere turns per pole of the armature reaction plus the ampere turns along the q axis, along q axis, correct? So ampere turns, so what are the things? Number of turns required on each interpole. So if I assume the total number of turns of the interpole is n interpole into the current, it is connected in series with the armature, so it will be Ia by capital A, right? As it is, okay, sorry, it will be connected, it will be Ia only, it will not be Ia by capital A, it will be Ia because it is connected in series with the armature, so it will carry the whole current Ia, correct? So yeah, this will be Ia only. Now per pole, right? Per pole will be divided by P. This will be equals to the number of turns in the armature, that is Z by 2, into the current per armature coil. Now this is the overall armature current, right? That is in series with the interpole. So winding carries the overall armature current. This will be armature current per coil. So Ia by A. This is the Ni, right, per pole. So I have to divide by P. Okay. Now plus additional q axis ampere turn that I have to basically remove, right? So this will be by mu naught. Okay. So this will be equals to like now I can directly find out the values. So I have to find out n interpole. What is IA? IA I don't know, but I can find it out from here, right? Roughly, like my IA roughly will be equals to IL, because nothing has been mentioned about the armature resistance. It will be equals to power 100 kilowatt divided by the Duso voltage. So this will be basically 10,000 divided by 2. So 500 amperes is the overall armature current. Okay. So and number of poles is 4. So this is n interpole. Armature current anyways I can cancel, right? IA by P I can anyways cancel here. So only this will be here only. Okay. So this will be equals to Z by 2. Z is number of conductors is 256. So 256 divided by 2 into 1 by A. 1 by A is number of parallel paths is 4. 4 as it is lap wounded. 4 plus Bi, flux density is 0.25. This will be 0.25 into LGI. LGI is 1 centimeter divided by mu naught. 4 pi into 10 raised to power minus 7. Okay, of course there is this number of poles. Number of poles is 4 divided by the overall current, that is 500. So this value I can directly find it out. So this will be 256 divided by 8. 256 divided by 8 is 32 plus this value. So this will be 0.25 into 4 divided by 4 divided by pi into 10 raised to power 5 divided by 2 10 raised to power 3 into 10 raised to power 3 divided by 5. So 15.91. Okay, this is 15.91. Correct? Am I correct here? Z by 2 is also there. Oh yeah, this divided by 8. Yes, it is correct. Yeah, this is correct. So this is the total number of interpole turns, right? Not per pole turns. So this is the total number of turns, 32. So this 47.91 is the total number of turns. Don't answer this. Okay, this is the total number of turns. Okay, total number of turns. So what will be the per pole? So interpole turns per pole, right? Because they have asked the per pole turns in each interpole. So each interpole is per pole turns. So basically I have to divide this by 4. So this I have to divide 47.91 divided by 4. So this will be roughly equals to 12. Okay, so 12 will be the answer in this case. 12 will be the answer in this case. So very simple and very easy to understand. So please keep this in mind that this value, right, this value is the, because someday you will ask, this is the peak AMF, peak MMF per pole, okay, across the armature. This you have to remember. So this very small things I say to remember. This you can remember. This is the peak EMF, peak MMF per pole. Okay. So yeah, I hope you have understood this like basic point. Let's solve another question. Let's solve another question. So this is the, I guess this is the last question, or any more questions we have? No, this is the last question. Okay, we're done after this. We are free. You are also free. I am also free. Okay, like it's like a task. So a compensated DC machine has 15,000 ampere turns per pole. So already they have given me Ampere turns, compensated ampere turns per pole already is given to me. It is 15,000. Okay, 15,000. Pole pitch to pole ratio is 0.68. So basically, pole arc to pole pitch. I think we have solved a question like this. So what I will do, I will give you this question as homework. Same question we have solved previously as well. So I want you to try this question out. In the next lecture, we will solve this question and we will start with the new topic, that is commutation. So if you have enjoyed this topic, if you have enjoyed this whole concept, right, trust me, anywhere in YouTube, anywhere in the paid classes you will see, nowhere you will understand this visually, like conceptually. Everywhere they will just tell you to mug up the formula. So I have tried to explain everything conceptually and visually, right, what is happening. So I hope you appreciate that. So make sure to comment down below in the videos and like the videos. So I will see you in the next lecture. Until then, happy learning.